And now, please welcome back to the stage, Stephen Jordan.
Okay, so back to the schedule, where we now have Zhou, who will tell us about quantum speedups in solving near-symmetric optimization problems by low-depth QAOA.
Thank you, Stephen, for the kind introduction. So today I'll tell you about this very wonderful work that I did with my collaborator, Ashley Montanaro, while I was visiting Phasecraft in Bristol, but I'm currently at UCLA. So this talk is concerned with the task of solving combinatorial optimization problem. So here we're given a cost function, C, defined over bit strings. And usually the cost function is written as a sum over clauses. For example, often like type of clause is a constraint clause, which is sort of evaluates to 0 if a constraint over a subset of bits is satisfied and 1 otherwise. So you can think about the cost function as counting the number of violated constraints. And as you can imagine, this is a very fundamental problem in many fields. And in fact, problems as wide as route planning and resource allocation and stock portfolio optimization, and many problems in our economy can be mapped to one of these combinatorial optimization problems. So because of their importance, it's of course a very big open question whether or not there's any quantum advantage in solving these problems. And in this work, what we are motivated to ask is, can there be an exponential quantum speedup in optimization by a low-depth quantum algorithm? So why the focus on the low depth, you might ask? Well, even with the advances, and there are many amazing advances in error correction recently, the quantum computer will still be limited to the low depth regime for a while. And a popular quantum algorithm that appears to work well in this low depth regime is the quantum approximate optimization algorithm, which I will briefly review. So the idea is to assign a qubit to each of the bit variables and initialize them in the so-called plus state. We then apply an alternating sequence of unitaries, one being the evolution under the cost function in the computational basis, and the other is a mixing unitary corresponding to a single qubit X rotation done in parallel. These operations are repeated over p steps according to some free parameters gamma and beta, and we measure the quantum state in the computational basis to get a bit string. By choosing the parameters gamma and beta well, we can try to minimize the cost function value achieved at the end. So the QAOA is an attractive algorithm because it's one of the simplest algorithms you can write down. And thus, it is very friendly for near-term implementations, and indeed has been implemented on a variety of platforms. Furthermore, the QAOA is very quantum because one can prove that you cannot classically sample from the output distribution of the QAOA, even at the lowest depth p equals 1, under reasonable complexity theoretic assumptions. Finally, a very important property of the QAOA to keep in mind is that there are parameters gamma and beta that can guarantee finding the minimizers and achieving the value C min as the depth p grows to infinity. Despite the sort of the various attractive qualities of QAOA, there are also many negative results about the QAOA, especially in the low depth regime, stemming from the fact that it is ultimately a local algorithm. For example, in the local regime where the graph underlying the optimization problem has bounded degree, recent work has shown that using the fact that the light cone in this setting is much smaller than the small graph, you can show that the QAOA is obstructed by symmetry for certain max cut problems in the worst case. And also, even in the average case, there's obstruction for certain spin glass problem that has something called the overlap gap property. Furthermore, even in the non-local regime, when the graph is fully connected or dense, the overlap gap property obstruction has been shown to persist in the constant depth regime, and this was later extended to the log depth regime using concentration arguments. Despite these limitations, there are still some positive results about the QAOA exhibiting small polynomial speedups over classical algorithms, which I would like to mention. For example, a recent work by my collaborators and I showed that for the problem of approximate optimization of Sherrington-Kirkpatrick screen glasses, the QAOA is able to surpass the best provable performance of any polynomial time classical algorithm. And furthermore, they appear to exhibit a quadratic advantage over in the approximation error compared to the best conjectural state-of-the-art classical algorithm based on message passing. Another work that was presented at QIP 2 years ago showed that the QAOA has a polynomial speedup over the best classical satisfiability solvers for random k-set problems. While the speedup here is a very, very small polynomial, it can be made super quadratic if you use also the technique of amplitude amplification. So in this new work, our paper presented some evidence that show that even in this low-depth regime, there still could be exponential quantum speedups. Specifically, we showed that even using just the one-step QAOA, you can actually solve many near-symmetric optimization problems, which I'll define shortly, in polynomial time. And in this black box query complexity setting, we show that for many of these near-symmetric problems, they can be solved with only a constant number of quantum queries using the QAOA, whereas a lower bound of n over log n classical queries is provably required. So that's sort of a super polynomial separation generalizing the Bernstein-Vazirani problem. And in the more practical setting of time complexity, we constructed many instances of random instances of these near-symmetric problems and benchmarked state-of-the-art classical general-purpose satisfiability solvers. And in the process, we discovered certain problems that seems to take all tested solvers exponential time, whereas we can prove that the QAOA solves them in polynomial time. So this gives us an apparent exponential speedup over general-purpose classical algorithms. So for the rest of the talk, I will delve into the results more in detail. And for that, I need to first define what I mean by a symmetric optimization problem. In a nutshell, essentially, we say that the cost function is symmetric if there's a permutation group acting on the input such that permuting the difference of the input relative to some secret solution string leaves the cost function invariant. This symmetry allows us often to write the cost function in a very simple form. For example, when the permutation group is the full symmetric group Sn, then the cost function is simply a function of the Hamming distance between the input and the secret solution string. To be more concrete, let's consider this following example Sn symmetric 3-set problem that I constructed, which I call the conjunction of 3n1 and 1n1. This is the conjunction of two Boolean formulas. The first, phi1, is the conjunction of all single variable Boolean clauses that are all negated variables. And phi2 is the conjunction of all three local SAT clauses, each with just one Boolean variable negated. So the first formula, you can see that it is satisfied whenever, if and only if the bit string is the odd-0 string. And phi2 is satisfied if the bit string is the odd-0 string or if the bit string has Hamming weight n or n-1. So if you write down the cost function, you can basically specify it in terms of the Hamming weight or the Hamming distance relative to the secret string. And you will see that there's two local minimums. One basically is the global minimum when the Hamming distance is 0. And another one that's slightly suboptimal with roughly energy n, corresponding to the Hamming distance of order n. So because of the fact that there's these two very distant local minimum, and whenever you guess a random string, you sort of land somewhere in the middle. If you look at this bottom right plot, there's the kind of a cartoon of the energy landscape. You will see that this type of problem is very challenging for local search problem because often if you pick a random string and you sort of try to do a hill climbing, you basically, or in this case hill descending, you're going to move towards the suboptimal local minimum. And this is also the case if you have simulated annealing. So our first main result shows that for this type of Sn symmetric problem, the QAOA is able to succeed to finding the hidden solution string with 1 over square root of n significant probability whenever the cost function takes on mostly distinct values. And specifically, we consider basically any SN-symmetric cost function where the cost is the function of the Hamming distance. And if you assume that the cost function is completely distinct, meaning that if it takes different input Hamming distance, you give distinct outcomes, or if it sort of violates this assumption with a vanishing probability, if you sample all the random strings, then the one-step QAOA is able to achieve a ground state probability of 1 over the square root of n using beta equals pi over 4 and a random gamma chosen uniformly. And I will just give some brief remarks on this result. So first of all, this sort of assumption of distinct values might think artificial. It has to be required to some extent, it turns out. And this is because if you consider the case where the cost function is 0 for the solution string, but uniformly 1 for the rest of the strings, this corresponds to the unstructured search problem. So as we know, there's a well-known lower bound of 2 to the n over 2 queries that's necessary to solve this problem. So that kind of implies almost that you need some kind of distinctness in your cost function in order for any sort of reasonable quantum runtime. And furthermore, this distinctness is sort of pretty generic. And in fact, in the example problem that I gave in the previous slide, you can prove the distinctness assumption by sort of showing that kind of a polynomial equation has no integer solutions using some number theoretic arguments. And it turns out that the proof of this theorem is actually pretty simple, so I'll just kind of go over that with you right now, and maybe it'll illustrate some intuition. So let's assume for now the secret bit string is just the all-zero string, and you can write down the overlap between the output QAOA state with the secret string as a sort of this combinatorial sum. So basically, ultimately, once you kind of do this explicit calculation, you can write down this sort of overlap as a sum over the different possible Hamming weight of all the strings, where each Hamming weight contributes sort of a phase that's proportional to the cost. And now if you kind of take the square of this amplitude and average over random gamma, you will see that there will pop out a cross term which vanishes unless sort of the two cost functions are distinct. And because of the distinct value assumption, this kind of forces the two the cross term whenever it has correspond to distinct kind of Hamming weight k and l, that vanishes. So the only term that is left is basically can be evaluated with the explicit summation that can be shown to be order 1 over square root of n. So it turns out that this 1 over square root of n probability can be kind of improved if you consider specific cases where the cost function takes on certain forms. So for example, given a SN symmetric cost function of the following form, and this is sort of applies to this 3n1 conjoined with 1n1 example that I mentioned earlier, we can show that the QAOA is able to succeed with a probability that's order unity with a gamma that's sort of vanishing like 1 over n to the l minus 1, l being the locality of your cost function. And you can also kind of consider more general settings. So we didn't explore all the possible permutation groups, but we consider, for example, a product permutation group as a possible symmetric kind of way of defining a symmetric cost function. And in this setting, we also show that for cost function that takes on these certain forms that has like multiple local minima, under some mild technical assumption that the QAOA is also able to succeed with order unity probability. To kind of briefly sketch these proofs, the idea is basically take this expression of the overlap of the QAOA state with a secret solution string, which, as I mentioned earlier, can be written as a kind of a combinatorial sum. And you do sort of a integral approximation and apply the saddle point method. And it turns out that for very specific choices of gamma, you're able to actually rigorously evaluate this integral and obtain a kind of a non-vanishing kind of probability in the ground state. So keep in mind that here we're no longer optimizing the expectation of the cost function at the end. We're optimizing the overlap with the ground state, which is could be very different. So while that it might appear that this assumption of symmetry is very important for QAOA to succeed, it turns out that the algorithm still works even when the symmetry is explicitly broken. So specifically, if you consider the case where we break the symmetry by taking a symmetric cost function, which is you write it as a sum over local clauses, and we sort of randomly sample each clause with some probability. For example, you can think of the adding a weight to each of the clauses, which is a Bernoulli random variable. This obviously explicitly breaks the symmetry, but it's sort of related to the symmetric problem, so we call these problems near-symmetric. So for these problems, it turns out that as long as the QAOA succeed on the original symmetric problem, then even in the sparsified setting, and you can actually sparsify extremely kind of sparsely in the sense that you can kind of keep each clause with kind of 1 over n to the L minus 2 probability, you can still show that the QAOA succeed in finding the ground state with order 1 probability. And to keep in mind what this actually means is that if you take a 3-step problem that has or a 5-step problem that has n to the 5 clauses, you only need to keep n squared clauses in the sparsified cost function, and the QAOA still works to find the ground state. So a key lemma that we use to kind of prove this theorem is to show that if you apply the cost function that's sparsified with an appropriately rescaled kind of gamma parameter in the QAOA setting, you end up with a quantum state that is approximately the same as the case where you have the fully symmetric cost function. So, well, we have shown that the QAOA seems to work quite well for these symmetric and asymmetric problems. It is still unclear how well does the classical algorithms perform on these problems. So for that, we kind of turn to sort of the classical algorithms world, where it turns out that there's annual competitions that are run to kind of implement efficient solvers for satisfiability and maximum satisfiability. So we picked just a few kind of recent winners of these competitions for both the satisfiability and the max kind of competition, as well as the max set evaluations. So these are some examples. And one of the examples, this walk set LM, for example, was found to be the best performing classical algorithm for random case set that QAOA had an advantage of in this the work that I mentioned that appeared in QIP 2 years ago. So let's start with an example that is sort of very similar to the earlier example, where we have a conjunction of sort of 3 local clauses with 1 negation and 2 local clauses with 2 negations. So again, this is designed in a way that the secret bit string is the global minimum, and you have a suboptimal local minimum that is sort of the sort of Hemingway distance n away. The energy landscape is sort of sketched on the top right corner of the slide. So here we're plotting the runtime on both the log-log plot on the bottom left and the log linear plot on the bottom right for the 6 different classical set solvers that we benchmarked. And as we can see, the walk-stat algorithm that was previously found to be the best competition for QAOA in the random case set setting seems to do quite badly in these sort of symmetric problems. But some of these other kind of competition-winning solvers seems to do quite well, although most of them, some significant portion of them seem to take exponential time, especially if you look at the log linear plot. But it turns out that this problem seems to be easy for a subset of the solvers, and this is apparent if you look at the bottom right plot, where we normalize the runtime by n cubed, which is sort of the number of clauses, the size of the problem in these SN symmetric set problems. And we see that the fact that the runtime, the normalized runtime levels off to a constant implies that this algorithm can solve these SN symmetric set problem in linear time. So then we move on to not fully symmetric problem, but near symmetric problem that we obtained by sort of sampling the clauses, as I mentioned before. And for these, we also introduced frustration to make the problem harder, so we then focused only on the max set solvers. And it turns out that although it seems to make the problem harder for some of the previous algorithms that had kind of almost linear scaling, like max CDCL, But one of the classical max set solver seems to still exhibit a linear time, linear improvement size runtime, as shown by sort of the normalized runtime on the log linear plot. The next trick that we throw at the classical algorithm is to sort of make the symmetry a little bit more complicated. So now let's consider the product group, Sn over 2 squared. So in this case, the energy landscape is sort of roughly can be written as a function of the Hamming distances in two different subsets of the strings. So this is a two-dimensional energy landscape, which allows us to have more local minima. And again, we kind of design a problem in a way where the secret string is the unique sort of global minimum. And in this setting, it seems like all the max set solvers that we tested take on kind of exponential runtime, even after you sort of rescale the runtime by the problem size. So in contrast, as we kind of mentioned before, for these problems, as it turns out, we can apply our theorem 2 and theorem 3 to show that the QAOA has sort of a linear runtime in the problem size, because you can solve them using basically one-step QAOA and measuring repeatedly. And on sort of this rescale runtime plot, you can see that effectively what that means is that the QAOA runtime is flat relative to the problem size. So in summary, what our result has shown is that for optimization problem with approximate symmetry, it turns out that QAOA, even at the lowest possible step, is able to use sort of very interesting interference effects to achieve order 1 or order 1 over square root of n ground state probability in many cases. And this implies that in the query complexity setting, only order 1 or order square root of n queries is sufficient using quantum query, where you can prove a lower bound of n over log n classical queries to recover the secret string. And by benchmarking a real kind of state-of-the-art classical solvers on kind of many randomly constructed near-symmetric problems, we found instances where there exhibits apparent exponential quantum speedup over general purpose solvers. Now, some very interesting open questions to address are, can we actually observe this speedup in practice? As I mentioned, you can actually take a very dense symmetric problem and sparsify it to keep n-squared clauses. So you can, in principle, implement it, kind of an example of this problem in the experiment and kind of validate the algorithm on a real device. And of course, it's also interesting to see whether or not these symmetric problems apply more real-world setting. And another interesting question is to kind of move beyond symmetry that only permute the bits. So we can also consider symmetry that acts on the bit strings directly, not just permuting the order of the bit variables. And the analysis of the QAOA, I should remark that is tractable as long as the size of the orbit of the symmetry group is polynomially bounded. And it will also be interesting to explore other ways of breaking the symmetry besides the sparsification method while retaining the success of the quantum algorithm. And most of the kind of the discussion I had comparing kind of the QAOA to classical solvers focused on general purpose solvers. And of course, if you have a classical algorithm that knows how we constructed the problem and knows the hidden symmetry, you could, in principle, construct Taylor algorithm that might have a better runtime. So we leave kind of an open question, like can we find design problems that can stump even this Taylor algorithm that know the existence of the approximate symmetry while still kind of allowing QAOA to succeed in polynomial time. That's it. I'm happy to take questions.
Thanks for the talk. So do you have an example of a query complexity speedup or a speedup that you conjecture exists in the case where the quantum circuit has constant depth?
I guess I'm not aware of that because I guess like for all the problems we applied here, like at least our results only apply when there's n-squared clauses, so that already implies that the depth is the actual circuit depth is n. But I think that's an interesting question. I think potentially, you can look at a more simplified cost function that, well, I think maybe it's possible to actually even show this if you have something like a one set. I think maybe it's actually. I mean, I think in that case it's sort of very similar to the Bernstein was around a problem. So maybe it's not as interesting, but that's a. I think there might be a way to show using like some kind of one set construction, but I'm not 100% sure.
Because then maybe you could complement your rigorous results with a problem where you have a depth lower bound for classical computation and a constant depth algorithm. I think that would be nice.
I agree. Thank you.
Thanks for the talk. I really enjoyed it. So I'm curious, just in general, in like the early days of fault-tolerant quantum computing, in general, with the potential quadratic speedup of QAOA, I'm kind of curious. Do we have any thoughts that after error correction, we'll get any advantage, or will error correction just eat away at anything that was achieved?
That's a very good question. I think that, based on our recent results, it seems like kind of quadratic speedup seems to be not too difficult to find. And, certainly with error correction will help, especially in the setting of if you care about approximate optimization. But I think while results here, what it really, the reason why it's exciting for us is that it seems like you can get, potentially exponential speedups, which of course, then it will, motivate us to actually, try to run QAOA in fault-tolerant mode. But I think that, it still remains to be seen if, there's a case that's like sort of, directly practically interesting to people, because like, of course, the examples that we constructed are kind of, designing in some sense, while still kind of also stumping all the classical algorithm that, knows, also potentially about the symmetry and so on. So I think like, but I think that, my belief is that, it seems to be, there's hope for like, large superquadratic quantum speedup and maybe super polynomial speedups.
Because one last question too. So for
All right, well, let's thank Leo once more for this very nice talk.